Agostina, do you want to say a few words before we start digging into the details?
Of course. Thank you, Sylvain, and welcome everybody to our webinar session. We're very excited about having you today. We will start soon, but first we will mention some points related to the organization. Your microphone is on mute. We will keep this feature as it is to provide an organized session to avoid background noise and interruptions during the presentation. However, we have a messenger option. In the bottom of the screen, you will see an icon. You can submit written questions by typing them in the question box in your control panel. We would like to have an interactive session and discussion, so please feel free to send your questions. You may send them at any time, and we will collect and address them at the end of this presentation. You will also be able to count with a presentation that will be shown during the presentation. It will be sent by email on PDF right afterwards. Now I would like to introduce our speakers. Mr. Rasmus Egeberg holds a Master's of Science in Physics from the University of Copenhagen and a PhD in Surface Science from the Technical University of Denmark. Since 2001, he has worked in R&D at Topsoe. He has extensive experience in fundamental surface science, hydroprocessing reaction mechanisms, and pilot plant testings. Mr. Søren Enevoldsen holds a Master's of Science in Chemical Engineering from the Technical University of Denmark and an Executive MBA from Copenhagen Business School. Mr. Enevoldsen joined Topsoe in 1988. He has an extensive experience in disciplines ranging from technical service, sales, and business development. Mr. Sylvain Verdier holds a Master's of Science in Chemical Engineering from the University of Pau, France, and a PhD from the Technical University of Denmark. He joined Topsoe in 2006, where he currently works as a Senior Business Strategy Manager in the Strategy and Innovation Group. About the company, founded in 1940, Topsoe is a global leader in solutions for a decarbonized world, supplying technology, catalysts, and services for worldwide energy transition. Topsoe's mission is to help partners and customers achieve decarbonization and emission reduction targets, including those in challenging sectors. Topsoe is headquartered in Denmark and serves customers all around the world. About Weibold Consulting, the company was founded in 1999. Over the years, Weibold gathered an international team of experts and established a large professional network involving researchers, decision makers, and authorities. To date, Weibold maintains license with numerous industry players, including world's leading innovators. This enables Weibold to receive first-hand information about markets, new products, and innovative technologies in the field of tire recycling and pyrolysis. In addition, Weibold issues a free monthly newsletter on tire recycling and pyrolysis, which relates to all aspects of these industries and provides unique takes on the newest developments and trends. We hope you enjoy this session. Rasmus, please, and Sylvain, whenever you want.
Ready. Thank you, Agostina, so much for the introduction. It's a pleasure to be here. We'd like to thank you and the Weibold team for organizing this webinar. So today we will talk about how to upgrade tire derived oil or tire pyrolysis oil. There are several names out there, as you know, and for fuel and chemical applications. So we had a great intro. Thank you, Agostina, again for that. Of my two colleagues, Rasmus, who is in R&D, experts in hydroprocessing, and Søren, who is now a licensing director, selling a wide range of our technologies. And Søren, thank you for your flexibility. Just so you know, Søren is in Japan as we speak. So yes, I appreciate you take the time for us today. And my name is Sylvain. I'll be the host today. Mostly Rasmus and Søren would be the speakers. Søren, what is the take-home message? What should people know in case they have to leave this webinar before the end of the hour? What should they remember?
For the introduction, and then I'll start out with the take-home messages. They will be repeated at the end. But the tire-derived oil that can be used to or be upgraded to produce naphtha, gasoline, aviation fuel, diesel, and marine fuels. So that is one take-home message. The other one is that the chemistry of the tire-derived oil is challenging because it contains aromatics and nitrogen, and to remove these to a low level, that's the key to upgrade the tire-derived oil. And the third point is that the technology that is used for this is hydroprocessing.
Yes, I think I lost Søren. I don't know if you have to, Rasmus.
He's very silent at least.
Yes, good. But
More than 50.
yeah, I'm sorry for this, but yes, I can take the last point. So hydroprocessing is indeed a commercially proven technology that is needed to upgrade this type of feedstock. Are you back, Søren?
Okay, you couldn't hear me?
No, not the last point, but I covered for you.
Okay.
So, yes, let's go through the agenda now,
Yes.
Søren.
All right, thanks, yes. And the agenda is as follows. There will be a few words about Topsoe. The second point is what is tire-derived oil actually made of, and which products could we make, and how can we make them, and then a short summary, and there will be time for questions in the end.
Yes, as Agustina said in introduction, we want this session to be as interactive as possible. So please do ask your questions and we'll take them at the end. We should have 10-15 minutes at least to answer them. So a few words about Topsoe.
A few words about Topsoe, yes. We are about 2,200 employees worldwide. As you can see, we are located in various strategic places, mostly within the energy related sectors or chemistry. We are number one in the world in renewable diesel, that is diesel from vegetable oils or waste oils. And ammonia, we are the by far largest licensor also worldwide. And also for hydrogen, which is a source for all kinds of upgrading of various oils. We are also the biggest licensor in the world. We are a technology-based company, so we spend around 9% of our revenue in R&D, and the revenue is close to 900 million euro, and we also make a little profit.
So what is it we do, Søren? We do not produce fuels or chemicals, correct?
No, exactly. We are a technology provider. We are a licensor. We provide the technological solution for these various plants, and we do the engineering design packages, and we deliver that to others to be implemented in the final design, and also for them to construct the plant. In order to make these processes happen, we are using our own developed catalysts, and in some of the processes, it's also necessary to have some special equipment, special features of the equipment, and we also supply that. Finally, we also, to make sure that the things work, we have quite an extensive technical service team, and we also do regular follow-ups on the plants, evaluating performance data, etc. That is also used as a feedback to improve our technologies.
Good, perfect. So that was all about Topsoe. We won't bore you more about us, but it was just to set the scene because we might be in different worlds or ecosystems. So it was just to set the scene a bit.
Yes.
Now Rasmus will enlighten us about what tire pyrolysis is made of and a bit of chemistry. For those of you who have not done chemistry for a while, you will have a nice little upgrade. Rasmus.
Yes, so we want to upgrade the tire-derived oil, and for that we need to know at least two things. What is the properties of the oil that we start with, and what is it we want to end up with? And first we look a little about the feeds, the TDO. So it is tires, and they have been through some pyrolysis process that's given. And the oil that then comes out is, of course, very much determined by the composition of the tires, and to a little lesser extent, the pyrolysis process. So the pyrolysis process, it's mainly the temperature and the residence times that may differ from pyrolysis process to pyrolysis process. But in our experience, it is not such a big variation that has on the composition of the oil. The oil reflects the composition of the tires. There's a large renewable biological component, you can say, of natural rubbers, and also a lot of synthetic rubbers in there, along with other additives, the composition of which is reflected in the oil composition. So one is the very aromatic nature of almost all the components. That also, so some of the structures are broken down, of course, but you still have the aromatic compounds left. You have the carbon black particles. Those are very hard to decompose, so they are also, even though some can be filtered away or removed in other physical processes, they will also remain to some extent in the tire-derived oil. And finally, I will also mention the nitrogen compounds. Organic nitrogen molecules are by nature quite hard to remove, and they are also inhibitors for other reactions, as we will come back to. And these also part of many of the added components in the tires to begin with.
Good. Okay, so the way we, I don't know if you know, but Lego is a Danish product. We don't work for Lego, but we like the Lego analogy. So here we're going to describe the properties of the tire-derived oil in 4 blocks. The first one is elemental analysis, and it's something we look at for fossil, renewable, and alternative feedstocks. So Rasmus, for this elemental analysis, what is key for you?
Yes, as it is written here, there are basically 5 elements, and the ones in red are the ones that stands a little out. And I would say, compared to our other experiences with both renewable and fossil feedstocks that need to be upgraded, and I would say, unfortunately, a little on the negative here, is that the hydrogen content is somewhat lower in the feeds than we usually see. That means that in order to end up with a fuel that has good qualities, at least a diesel fuel that has good fuel qualities, or also for aviation fuel, you need to add hydrogen. So you need to add a considerable amount of hydrogen, I would say, and that is something you have to consider when you design your process. And then the nitrogen, also quite high values here, and as I alluded to, these nitrogen compounds, they make all the other processes more difficult because they are inhibitors. The sulfur is not the biggest problem. The catalysts are able to remove this sulfur quite easily, and the oxygen also in so low amounts that it's manageable.
We'll come back to that, but typically in a product, Rasmus, in terms of hydrogen content, like diesel jet, we're around 13–14%, correct?
Yeah, I mean, basically the ideal is CH2. That's the ideal, and then you are close to 14%, but a little less can also do it, but it's in that range, yes.
Exactly. And then nitrogen, it's indeed high. Maybe for you, you are listening to like 4,000 ppm. What is that? It's actually on the high side, but we'll come back to that later. Okay, so that was elemental analysis. So that's something we look at. If you send us tire-derived oil, those are analyses we would do to get a feeling of how is it to upgrade, depending on the product you want to do. Okay, bulk properties. So here for us, it's SG's density, cloud point viscosity. It's more the physical properties. And here, Rasmus, what stands out exactly?
Yes, and also these properties are important because they are the basis for the specifications that controls whether the finished fuel is living up to the standards or not. And here, for instance, the density in Euro 6 diesel has to be below 0.845, so you have to reduce the density quite a bit. But what stands out again in red is the total acid number, much higher than for usual fuels that have usually lower than 1 in TAN in distilled fuels, at least I would say, that are to be upgraded. So that acid number here, that puts some requirements on the selection of materials all the way through the process. Of course, when you do the hydroprocessing, you reduce the TAN. So in the end of the process, the requirements are not so strict as in the beginning. Nevertheless, these are high numbers, so you have to consider this. And then the sediments, as I mentioned, the carbon black particles, they may be broken down, and maybe the size distribution is not the same as in the tire it was, but they are still there. And 1% means that you have physical particles that will clog up your catalyst bed very rapidly if you do not remove them. So you need to do some filtration or other means to remove the sediments down to much lower levels in order to have a process that can run for months and years.
This TAN of 2 to 10, and we'll come back to that, it's not unheard of. We have commercial plants running with TAN of 150, 200 for some renewable feedstocks, and the same for sediments. So it's not unheard of as well. I think what is
it's not unheard of, and there are solutions and proven solutions even for all of these things. It's let's say a new combination of proven solutions that you need for this derived oil.
Yes. What we call contaminants, which is contaminants for us, for our catalyst, basically what will deactivate, plug, or inhibit catalyst. So here, Rasmus, do you want to say a few words about all of those in red? So
they're all in red, yes. And I want to stress again that it's not the pure metals we have here. It is these metals are part of organic molecules that are oil soluble. But the issue with these are that they all poison the catalyst active sites quite rapidly. The arsenic you see is in ppb, parts per billion. So you would say, okay, very small numbers, but the arsenic has the unfortunate ability to very specifically titrate actually the active sites and sit there and kill them permanently. The other metals have not quite as bad properties, but the amounts when you go into ppm means that you quickly build up on the order of 10, 20, 50 weight% on the catalyst quite rapidly. So you would need to change out the catalyst. They kill the catalyst, albeit slower than the arsenic does. So the solution to this is to design specific guard catalysts that have high uptake of these metals and do not, as such, are not poisoned in the same way. But basically, this means extra reactor volume needed for this, and extra catalyst that you can then maybe change out more often than the bulk catalyst. These catalysts are also cheaper than the bulk catalyst. But at some points, even with that solution, the amounts are so high that it's hard to see the sense of it and the economic sense of it. Other pre-treatment processes may be needed in order to lower the levels depending on where they are.
We have seen similar level of contaminants, let's say for plastic pyrolysis oil, for spent lube. This is not unheard of as well. It's just, again, a different combination, as you said, Rasmus. Last but not least, it's about distillation curve and composition. So let's start with a boiling curve, distillation curve. So what is this 200, 370, 370 plus? What is it, Rasmus?
Yes, so that means that if you fractionate the tire-derived oil as it is, then around 30% will be boiling below 200 degrees. And this is more or less the boiling point area for naphtha and gasoline. So if all the other properties were on spec, which they are not, then you could expect around 30% gasoline yields. And the next part from 200 to 370 is kind of the diesel range. Also in this range is the jet fuel range. So that's the lower, let's say 2/3 of this range from 200 to 300 in rough terms. So this is the yield you can then expect of this type of fuels. And finally, boiling above 370 is what you could use for marine fuel, which is then higher than the diesel boiling. So these give some rough indications, and it is very rough, and it also changes during the upgrading, as we will come back to. But it just gives you an idea about what we're talking about.
Yes, as Rasmus said, during the hydroprocessing steps, depending on the design, layout, and catalyst, we will move that boiling curve. So this is again just what you have in the feedstock. Okay, aromatics, diene, bromine number.
Yeah, so let me start by the diene. So this is a measure of the conjugated double bonds in the oil. And these are important because they are precursors to forming aromatics and coke. So in order to basically, if you heat up the oil as it is, it will very quickly polymerize, and it will not only form coke on the catalyst, but also in itself, you can say. So you need to saturate these conjugated double bonds at a low temperature. So that's usually the first process steps, especially with these types of values of diene number. And then after that, you are left with still single double bonds. That's measured by the bromine number. And these also need to be saturated in order to make a good diesel products. They are not so bad. So olefins for the gasoline, for the octane number, they are actually beneficial. So it depends a little on the products you want to make or what you would do them. But typically, we would also saturate these. These are also not so difficult to saturate. And then we come to the aromatics, which is a very high percentage here. And this is also, again, a double-edged sword, that for gasoline, it's usually a good to have a lot of aromatics, whereas for diesel and jet fuel, it is good to have a low amount of aromatics. And to saturate all of these aromatics, we need to, first of all, consume the hydrogen I mentioned earlier. That also goes for the diene and the double bonds in general, but more is needed for the aromatics, and also that these aromatic saturation is hampered by the nitrogen molecules.
Good. Before we move to a poll for our listeners, just a question about the diene value and this thermal instability. So this is also something we've seen in, like, I think coke and naphtha has that in.
Yes, coke and
right,
naphtha, FCC naphtha. Yeah, we have our coke oven tars that we also have a process for upgrading. So it's not unheard of, these values, but you just need to be aware of what to do about it.
Good. So that was all about chemistry. So it was just a little refresh, and just to explain you how we look at it. So we look first, of course, what we have, and then what we want to do, which would be the second step. But it's time to engage with you. You also have to do a bit of work here when you listen. So in a minute or so, Agustina will launch a poll, and you'll be able to click. But the question we have for you, we'll have about a minute to answer, is which property is a main challenge for you when it comes to upgrading tire pyrolysis? So we explained a bit. It was just to see if you listen. There is no prize to win, I'm afraid. Is it number 1, sediments, number 2, nitrogen, number 3, aromatics, number 4, high end boiling point, so meaning the feed is too heavy, and number 5, the high acid number, this TAN number that we described? So please, you can answer right away as you wish. Let's see, I can see people start answering. Very good. We give you about a minute. So, and when you talk to customers who want to upgrade tire derived oil, is there a specific concern they have in terms of properties the first time you talk to them, or what is your impression of it? What have you heard so far?
in relation to the properties.
Yes, is it something they are worried about, or they're mostly talking about the products they want to do out of it?
They are mostly talking about the products that they want to make. And yes.
Good. Rasmus, which we don't want to show a disclaimer, but either property that's not here, that's also worrying for you, or something you think about when you run a pilot test, for example.
I think it covers it pretty well. I mean, you didn't have all the metals here. I would say that is one point where it is not so much a worry in the pilot test, because the pilot test is relatively short, and this is something that builds up on the catalyst over longer time. But it is something for the arsenic, it is something that could actually influence the pilot test if you do not also use the guard catalyst there.
Good. Well, time is out, so let's look at the results. Agustina, can you show the results?
Yes, I have just shared the results.
Okay, good. So the main one, so no answer 36 because of time. So we have more or less equal nitrogen aromatics. People have been listening, so in Erasmus, just so you know. Then we have sediments, high in boiling point, and high acid number. Good, but it's pretty accurate. And there's not one, like all of them are important, but as Erasmus mentioned, like nitrogen and aromatics are really key in terms of reaction. Cool. Well, let's move on to the next slide. So, on this table, we are comparing tire-derived oil with other type of feedstocks. So do you want to say a few words about this, maybe?
Yes, we can say a few words. If we say, look at the tire pyrolysis oil, we start from the top with hydrogen. The hydrogen content is around 10%. And as we mentioned earlier, or Rasmus mentioned earlier, we want to end up with 13, 14%, depending on the product that we want to make. So it means that a lot of hydrogen needs to be added. The low content of hydrogen, comparatively low, also has to do with the high aromatic content. So when we go in the process, it will be mentioned later, but then there will be the hydrogen consumption, creating an exotherm heat release, and that needs to be incorporated in the design. We also have a little bit of oxygen. It's not a big concern, but anyway, there will be some water formed in the process, and that needs to be also taken into account, especially if we have halogens like chlorine and bromine. It also has to do with the metallurgy that is used and the solutions that is used to wash it out. And then the nitrogen content, as mentioned already, it's quite high. And it's also nitrogen is an inhibitor on the catalyst to hydrogenate aromatics. So basically, if we want to make a lighter product, we want to get the aromatics saturated. In any way, we want the boiling point to go down. If we want to make diesel, we don't want aromatics, because aromatics, they have a poor cetane number. So in any case, we need to remove the nitrogen content to a low level to get the boiling point curve lower, to get the density down, and also so it's really a key to getting a good product. Then we have contaminants. Yes, if they are high weight ppm, it requires some pre-treatment, and the same with the fines. And as mentioned, the hydrogen consumption is quite high compared to what we see for other processes. You can say vegetable oil is also high, but there's also we also need to make special features in the design. One area where we actually see a lot of similarity in the composition in relation to chemical composition with aromatics, etc., is for a coal tar made from what is called medium temperature tar. It's a lignite coal-based pyrolysis oil from tar, and we have worked with that lot in China. Both Rasmus and I, we've been working for several years on that, and also have a number of industrial references in that area. So we have an industrial base to see what we can achieve.
Yes. We can say to our knowledge, there is no industrial plants upgrading tire pyrolysis oil to make fuel right now. Oh, maybe there is some out there, but yeah, we never heard of any. But again, tire pyrolysis oil is a combination of things that are done industrially. So it's just about finding the right blocks, or just.
Yes.
Not just, but yes, almost.
So these are some of the considerations that we make when we look at these feedstocks.
Good. Okay, now let's look at the type of products we want to make, Søren. Is that okay with you?
Yeah. Yes. And it's a little bit along the same lines. So if we take the composition on the left, it has already been mentioned. If we want to make gasoline, then we have a maximum endpoint point of 210 approximately, and the density needs to come down. And in order to do that, we both need to hydrogenate, but we also need to crack, obviously, the endpoint point. We need to break up these molecules to be shorter, to do a lot of things there. So if we go for jet, it's not as strict, but still maximum 300 degrees endpoint point, and that is an absolute limit, by the way, with a density and a maximum aromatics content of 25% in the finished jet. There is no standard yet for jet from tire-derived oil, so it needs to be going through all approval processes to do that. And diesel, similar thing. We have 360 maximum endpoint point. We can also get there by cracking or by accepting that there is an amount of unconverted oil left. And the density requirement is not so easy to achieve. So we can make diesel, but it will not be a fantastic diesel. It will probably be a blending component. And then for marine fuel, obviously it can be used.
Yes.
So really.
Good. Any other properties you want to discuss here, or should we move? I think we can move to the next slide. Søren.
I think we can move on.
So here it's, yeah, I think people heard it several times already, but yeah, one last one for the road, nitrogen and aromatics.
Yes, we have the nitrogen aromatics discussion again, and it's quite central to understanding what products we can achieve. But I probably don't need to say so much more about that.
Perfect. Some of the questions we ask, it's not only to make fuels out of tire-derived oil, but so can it be a feed to make plastic? Basically, is it a feed that could be sent as such, or maybe not, to a steam cracker to make ethylene and propylene? So what do you say here, Søren, when somebody asks you this?
To say that everything is possible. It's not the most fantastic feed for a steam cracker, again, because of the aromatic content. So we need to saturate the aromatics, which is quite a task, especially when we come from these very high levels with a high nitrogen. But it obviously can be done with some cracking, but also with the potential of big yield loss to gases, that's fuel gas.
Something we often say is that dilution is a solution sometimes. So although it's not the best feedstock, if you dilute it, you use very little and you dilute it in a lot of proper feedstock for steam crackers, this could limit the poor properties of this feedstock. Rasmus, before we go to the next slide, do you have anything else to add to this discussion about steam crackers?
No, I would say the yield loss is a little less concerned because basically the steam cracker takes everything except methane, and we do not crack into methane. That's not how the cracking catalysts work. But I think the aromatic and also you can saturate the aromatic, you can still have naphthenics. They are also not good. So it is not really suited for steam crackers, I must say, the chemical. But of course, it is possible to do something, and maybe in dilution you can overcome the issues.
Yeah. Here we wrote typical feedstock properties for steam crackers, but each steam cracker is different, like in terms of end boiling point, in terms of contaminants. So you really need to, I think, our experience, you really need to talk to the owner of the steam crackers operator to say, okay, what are your specs? What can you accept? So good. Okay, it's time for a little poll again. So you will have a minute. I will tell you, Agustina, when you can launch it, so people have time to answer. So yes, if you're working with tire-derived oil upgrading project, maybe that's why you're here listening to us today. What is the anticipated capacity? And I know the numbers are maybe a bit higher than what you think, but will you have less than 10,000 tons per year of TDO, between 10 and 50,000 tons per year, 50 to 100,000, more than 100,000 tons per year? Not relevant. You can start the poll, Agustina, and we have 30 seconds left. Hurry up. And what is a typical capacity to upgrade renewable feedstock, such as we mentioned waste oil and fats? Are we below 100,000 or typically 100,000?
We are above 100,000 for waste oils and fats and virgin vegetable oils.
Yes, like 100,000 would actually be on a small scale for renewable fuels. And then for fossil hydrotreated, it would be very small amounts, actually, all on the small scale. Rasmus, for plastic, upgrading of plastic pyrolysis oil, which scale are we talking about typically?
It's also, I would say, maybe between 500 and 1 million ton. I think the commercial scale plants that are planned that I know of are on that range, so also much larger than this.
Okay, good. Let's look at the results. I don't know if you can see the results. Yes.
Already ready.
Good, perfect. Okay, I cannot move because of the pointer. So Rasmus, do you see the numbers? Can you enlighten?
Yeah, so we have, let's say, most skewed to the smaller parts with 7 and 11 on A and B, and only 7 together on the latter 3.
Yes.
So, so certainly small plants.
Yes, and it's not a surprise for us. We just wanted to let you know. So yeah,
I can add. We are working on some commercial projects, and they are in the order of 80,000 tons per year. But these are first generation plants, and you would probably not go a lot lower than that to make it economically feasible.
So it's to upgrade tire-derived oil, correct?
Yes.
Yes. So I guess they have different pyrolysis plants, and they're gathering the oil and then upgrading it in a.
Actually, here it's at the end of one.
Okay.
In facility. In both cases, it's facilities, and then that range.
Good. Yes, it was just to challenge you who are listening. Like, when does it make sense in terms of capacity? We can design any plants, but yeah, of course, there's an economy of scale. So yes. Okay, but how could this be done? So you have all this amount of tire-derived oil. You have decided you want to make diesel, marine, I don't know, or fit for steam cracker. How do you do this? Again, we're back to the Lego analogy, and here we go through the different catalysts. We address the feedstock properties, and here it's not one catalyst, but several we need. I'll put all of them, Rasmus.
Yeah. So, so the first catalyst we let the oil meet is the grading catalyst, which is actually a Topsoe invention some 50 years ago, I think, developed in order to remove the physical impurities in the oil for them not to dictate the cycle length. So here it would be the remaining carbon black particles or other physical particles that would otherwise clog up the catalyst bed and lead to a pressure drop over the reactor, meaning that you would at some point have to shut down and replace all the at least the problematic areas only due to these physical particles. So the grading catalyst has a higher capacity for these and is able to take up the physical particles without a resulting pressure drop until at some point also they become saturated, of course, but that's the idea, that they can take up a lot more. And then the guard catalyst, as I mentioned earlier, they are the ones who have some kind of a chemical reaction with the oil-soluble metallic compounds, thereby trapping the metals on those catalysts, having a high capacity for those metals, so as to again be able to run the process for a long time without the contaminants slipping onto the main catalyst and poisoning it. The main catalyst is mainly doing various hydrogenation or hydrogenolysis reactions. So they are developed to remove the bad actors, sulfur and nitrogen, and to saturate all the aromatics that are there. And they are specifically designed for these, and they have been in both, at least similar catalysts have been in both fossil and renewable services, where they have proven their worth. So it is not the biggest uncertainty, I would say, of the process. And finally, the upgrading catalyst that I would call a dewaxing or a hydrocracking catalyst is to further refine the properties, so you can only go so far with hydrogenation, and at some point you need also, if you need some cold flow properties, you would do the dewaxing. If you need further improvement of the density, you would need some hydrocracking. So a little depending on what the properties is that you are targeting, we have a series of upgrading catalysts to solve these problems.
And how does a plant look like? So it's
Yeah.
not a complicated flow sheet. Sometimes some
No.
of our colleagues call it a baby flow sheet.
So it is very much a block diagram here, showing the different steps that needs to be there, and it's not it's basically in this order, but there's a lot of equipment that is not shown, so don't take it for more than it is. But as I said, we start by this stabilization of the dienes of the conjugated double bonds at low temperature. And then we would go to a little higher temperature, where we start by trapping the metals on the catalyst, on the guard catalyst. We go to the main hydrotreating reactor, where we do, again, saturation, removing of nitrogen and sulfur, and saturating aromatics. And then finally, some conversion where we do dewaxing, hydrocracking, in order to also get the boiling point distribution, not only properties, but it may also be boiling point distribution that we require. And then there's some kind of separation afterwards, not only in gas and liquid, but also some kind of fractionation by boiling point of the products.
So, Rasmus, we don't need 4 reactors to upgrade tire derived oil, or do we? Or it's more the functionalities we're addressing?
Yes, it is more the functionalities. So these may be individual beds in a single reactor. It may be more realistic, say 2 reactors that we use with 2-3 beds in each, and then distribute the catalyst over all of these beds. There may be some recycle. Also, there's definitely a recycle of the hydrogen. There's a big there's a higher amount of hydrogen injected than what you chemically consume, and the remaining hydrogen you would separate and recycle. But also the liquid products, there may be a benefit in recycling some of that.
Good. Okay, and here's the last slide before the summary and the discussion is some pilot test data, so something we can show. So here, Rasmus, what is it we see exactly?
Yes, so this is a sample of some of the data we have obtained in our lab here, where we do various upgrading tests. The pilot plant is shown in the schematic, where we just have a single source of a pump to feed and mix it with hydrogen, and a single reactor with a single bed. And then we do separation of gas, and TLP is the total liquid products. We have then afterwards offline been fractionating the sample, and those are then the graphs showing the properties of the diesel products. So in this case, it was a project meant to produce reasonable quality diesel, I would say. And this test was preceded by another test where we did the hydrotreating alone and removing the nitrogen down to very low levels. So you can also see on the graph that actually we start with a one ring composition at say 10% when you have zero conversion. And on the x-axis, the 390 true conversion means how big amount of the material boiling above 390 is converted during this part of the test. So when you convert, maybe you have around 20% of it, and if you then convert 50, you have 10% remaining. But what we're seeing here is that as we increase the conversion, we reduce the amount of monoaromatics. So we can also, after the hydrogenation is finished by the cracking reaction, we can further reduce the aromatics. And the aromatics is very closely linked to the density in that the both the hydrogenation of aromatics lowers the density, but also, of course, the cracking of larger molecules to smaller molecules will lower the density. So you can see that we are here able to go below the 845 in the density, which is the diesel spec, but of course here at the expense of the yield of the diesel products. So the higher the conversion, the more you crack, and also the more you crack down below the diesel range or even into gases. The pie diagram shows a sample. It's very dependent on the feed properties, the degree of conversion, and what you're trying to achieve. But all in all, this shows some of the data we can obtain from a pilot test, which will give kind of input to an economic valuation. So what is the expected yield when you reach the required product quality?
Good. Thank you, Rasmus. Søren, it's time for the summary again.
Yes. Again, like we started out by saying, the tire-derived oil can be used to produce naphtha, gasoline, aviation fuel, diesel, marine fuels. And the key here is aromatics and nitrogen. We saw just before that we need to reduce the aromatics content by, or the nitrogen content by maybe a factor of 5,000, from 5,000 to 1 to get a satisfactory saturation of the aromatics. So it is quite a significant reduction. We have hydroprocessing technology to do it. It's commercially proven, and we also have pilot tests that will enable us to design, to design plants. We just move to the next slide, because what we can say is that we have, of course, a significant experience with hydroprocessing of all types of feedstocks. I don't think you can find any company in the world that has as versatile as an experience as we have, that has been worked as much on the scientific basis in depth with the technology challenges there are. So we have all the fossil bases. We have hydrocracking, VGO. We have coal tars that are very similar to this. We have done a tremendous amount of work in that area. And we also have the renewable feed bases, where we are using all kinds of mysterious feedstocks. Liquid hydrofraction is not mentioned here, but that's another one of sewage sludge and others that has an extremely high content of nitrogen. And we also have plastic pyrolysis oil that we are processing. What we're doing, the way we are working, is that we typically get a feed analysis from a client. We will see what is the chemical composition, going back to the initial stage, boiling point curve, etc. And then from that, we can make an estimate on where we are at and what we can do. If the project moves on, we can do pilot testing in our facilities. We have around 100 pilots in our R&D facility in Denmark that can do tests. So from that testing, we are actually able to design a plant, a big industrial plant. It's a specialty that we have developed over many years. We can also do after the pilot test, we can also do a study, and that could be if it's a case of a revamp of an existing unit, or if it is a completely new facility where FID is required or similar. Then we go into the project phase where we will provide license, process license, and also the basic engineering design package. And based on our catalyst, we can then provide the guarantees in the finished plant. Then when the basic engineering design package is finalized, it can be sent to a contractor that will do the detailed engineering and construction of the plant. And as mentioned before, in the beginning, we will then do the supervision of the startup, loading of catalysts, etc.
Good.
Yes.
Thank you, Søren. So we have about 10 minutes for questions, and we have quite a few. So I'll start with, first of all, thank you both, Rasmus and Søren, and thank you for listening, dear listeners. First question is for Rasmus. Which pressure and in general operating conditions would you advise to upgrade to hydroprocessed tire-derived oil? And I guess the answer is it depends.
Yeah, it depends. I would say that usually in the upgrading part of it, where we use our conversion catalysts, we would typically use a somewhat higher pressure than in the first section. But again, pressure is good for the saturation of aromatics. So I would say somewhere between maybe 80 bars up to 150 bars, depending on what degree of saturation you are interested in, and again the properties of the feed. So it depends a lot, especially on the feed properties, I would say.
But we're talking mild hydrocracking level of pressure.
Yeah.
Not diesel, not fossil diesel hydrotreating.
No, I don't. That will not do it alone. Not for saturating to these high amounts, high degrees, and also the amount of nitrogen you need to remove. And also, even when you remove the nitrogen, you still have ammonia that is a much milder, but still a poison or an inhibitor, I should say, to the catalyst. So somewhat higher pressures are needed.
Perfect, thank you. Søren, question for you, and I'm not sure we can disclose this. Are we working on any commercial projects to feed directly the tire-derived oil to steam crackers? Or I mean upgraded tire-derived oil to steam cracker, or is it mostly to make fuels?
I can answer that quite easily because we are not for steam crackers. Tire-derived oil for steam crackers. We are working on projects to make fuel, but not all the way down to steam crackers.
Yes.
So I would also say that adding to a little to what Rasmus said, that what we have done when we have done pilot testing, if we really want to get low in aromatics, then we probably need to go even higher than 150 bar. That's at least what we have seen in our pilots. So
good. Thank you, Søren. Rasmus, back to you. It looks like the diesel that comes out of the upgrading section is not super. Just quoting. Can the diesel be diluted into good diesel to keep the complexity of the process low? So can you just blend it? Can you put it in the diesel pool, and that's good enough? Or do you need to produce on spec diesel?
it is partly a political question that I may not be the best to answer, but from a technical point of view, it is certainly a possibility, and it is actually the target of one of the projects, at least one of the projects we've been working with, where we have exactly looked at this and scrutinized what are the solution ratios needed in order for the finished fuel to meet. And you can say usually there is some giveaway in other diesel components that you have available. So maybe they are somewhat below the density limit. It's not for fossil fuel usually the limiting spec. It depends on what you have to blend with, of course, but usually there is some room there, and it makes really good sense, I think, to blend the tire-derived diesel with another slightly higher quality components.
Good.
And if I can add here, it's also when you make a plant like this, it could also be an objective to avoid the hydrocracking step, because it's both it's a high pressure hydrocracker. It's not that easy to either get permission for nor to operate. So an objective could be to take the hydrotreated.
I lost Søren.
Yeah.
So okay, I guess yes, it's said we might not need the hydrocracker. So it depends again what type of product you do. Okay, Rasmus. Yes, we lost you, Søren. So we're moving to question 4. Rasmus, this is for you. I can also take it otherwise. In the take-home message, so somebody was listening very carefully. We wrote TDO could potentially be upgraded. That is, does it mean it's a rare practice? So my question is it, do we know of any commercial or industrial plants doing hydroprocessing of tire-derived oil? And the answer is, as we said,
no.
No. So to our knowledge, no one is doing this commercially. So that's why we said potentially. Again, it's mixing things that are done with different feedstocks, but combining this setup is not done commercially to our knowledge. Søren, do you agree with that?
Completely.
Good. Okay, question number 5. It's actually a good question. All of them are good. But this one is, do we need pilot test for all the feedstocks? Or do you see a wide properties of tire-derived oil? Or can we basically, Søren, in your slide, we mentioned analysis, pilot testing, and study. Could we directly go from analysis to the study, or do we need to run a pilot test every time?
I think for this new feedstock, we would feel more comfortable if we make a pilot test, especially if we're going to design a complete plant. But we have made pilot tests on different tire pyrolysis oils, and they are not that different in composition, you can say. So you could, I hate the word in principle, but in principle, you could utilize the data we already have. But if we're going to design a complete plant, then we would be more comfortable with a new feedstock like this to make a pilot.
Good. Okay, we have 2 minutes and a few questions to go. What would be the investment and operational cost to upgrade tire pyrolysis oil to acceptable qualities? We knew this would happen. Søren, is there any numbers you can share?
Really share those numbers now, but it will not be cheap.
No.
I didn't actually know that.
Yes, but yeah, you can contact us again through our LinkedIn or through Weibold.
We look at the capacity, then we can provide a number.
Yeah, exactly. But the more it's economy of scale, so the larger the plant, the more tire-derived oil you have to upgrade, the lower, of course, the cost would be.
And again, if you want to do the hydrocracking step as well to get the last bit out of it, then it will add significantly to the cost. So it really depends on what product we're aiming for.
Yeah, exactly. Okay, 2 more questions. Rasmus, could chlorine be an issue for the equipment?
Yes, I mean, yes and no. It is an issue, but there are also solutions to take care of it. It is relatively easy converted to hydrogen chloride, but when you have a water phase present, you of course need to handle it. But I would also say that it is not the biggest problem. So we have other feedstocks where we have seen similar, and we have other feedstock where we're seeing much higher numbers of chlorine. So it is manageable.
Good, thank you. I'll take the last question. It's about kerosene. So the jet fuel produced out of the plant is not approved right now in the STM D7566, which gives the specs and the process for sustainable aviation fuel. But some people are working on preliminary discussions to have this approved as a pathway. So I think within a couple of years, depending on which tier they would go for, I imagine that this would be approved as SAF, sustainable aviation fuel, but this would not be Jet A1 because it's not made of fossil. So it's a different specification. But if you listen to our podcast, it's something we discussed about in our podcast. It's time, a minute too late. I'd like to thank again our speakers, Rasmus and Søren, for all your time. Agustina, thanks a lot for your help. It's early in Buenos Aires, so I appreciate you woke up so early. And then that's what we had for today. So the webinar will be available on the website. And as Agustina said, the PDF of the presentation will be sent to people who registered today. Agustina, anything else you want to say?
Thank you, Sylvain. Thank you, Rasmus. Thank you, Søren, for your presentation. And thank you, everybody, for taking part in the session. We would very much appreciate if you could help us keep our service relevant by giving us your feedback. So we will send you a form with a few questions very soon, together with a presentation that was shown during the conference. If you want to learn more about these topics, please kindly note that we are issuing our free tire recycling newsletters once a month. Also in our Weibold Academy section, you will find a wide variety of articles that highlight the different aspects of managing the tire recycling and pyrolysis business. If you have any questions related to the webinar or our consulting services, please do not hesitate to contact us. Thank you all and have a nice day.
Thank you, everybody. Bye-bye.
Thank you.